This is the CSEG Distinguished Lecture for 2009-2010. It's a short version of the lecture, which was presented at the CSEG Annual General Meeting in Calgary. And because it's a short version, I'm going to be concentrating mostly on the hydrocarbon examples because most of the people in the audience will be more interested in those. So there will be some examples from expression and water expression, and because most of the people in the audience aren't familiar with Airborne Electromagnetic methods, I'm going to start with the tutorial. Starting off from the very basics, all geophysical methods take some form of measurement, and that measurement is used to infer some physical property of the rocks. In some cases, it's not just the rocks that the physical property relates to, it's also the fluids that are in the rocks, and I'll show you some examples of that later on in the talk. So I'm going to start with some elementary physics, and hopefully some of you are familiar with Ohm's law. Ohm's law says that if you have some material of length L, and each end has a surface area A, and you apply a voltage difference between one surface area A and the other surface area A at the other end, then current will flow through that material. And if you take the applied voltage and divide it by the current, then you end up with a quantity called the resistance, which is indicative of the physical properties of that material. Now it turns out it's not quite that simple. So if you go to the next slide, you will see what happens if you make the material twice as long. So now it's got length 2L, and if you apply the same voltage difference in that case, you're trying to force the current through twice as much material. So it ends up that you have half the current flowing through that material. So when you take the voltage divided by the current, you get a different value for the resistance because you've changed the length. If you change the surface area, in this case, put one block of the material on top of the other, so you have twice the surface area. Now, applying the same voltage difference, you can get twice the current flowing through as the first case. So it turns out when you divide the voltage by the current in this case, you get a different number again. So you can see that the resistance isn't an intrinsic property of the material, it's more a function of the shape of the material. So if we want to have an estimate of something that gives you an indication of what the material is, then we need to remove that dependence on its shape. The way that you make a quantity that is independent of the shape is you take the resistance, voltage divided by current, and you multiply by the surface area and divide by the length. And then, instead of having a resistance in ohms, you have a resistivity in ohm meters, and that's independent of shape and an intrinsic property of the rock. Instead of multiplying the second equation by area and dividing by length, you can do the same thing. You can divide the top line by length and divide the bottom line by area. And voltage divided by length is just an electric field E, and current I divided by area is just a current density J. So the previous equation is also the same as the second equation is also the same as the last equation, which is resistivity is equal to the electric field multiplied by 1 over the current density. And this is Ohm's law for rocks. Now I've rearranged Ohm's law for rocks on the second line, so that we have the current density J on the left-hand side, and the current density J is proportional to the electric field E. So that if you increase E, you increase J. If you decrease E, you decrease J. The constant of proportionality is 1 over the resistivity. And this constant of proportionality is so important that we call that a special name, the conductivity. And it's important to remember that conductivity is just the inverse of resistivity. So sometimes in this presentation, I'll talk about conductivity and sometimes I'll talk about resistivity. One's just the inverse of the other. So that's Ohm's law. Another important law to understand in electromagnetics is Ampere's law. And Ampere's law tells you that if you have some current density J, denoted by these three black lines flowing from the bottom left to the top right, then circulating around that current density J will be a magnetic field, a circular magnetic field H, as denoted by these dashed red lines. The mathematical form of Ampere's law, written with vector calculus, is down the bottom here for those that are interested in the calculus. There are actually two types of magnetic fields. There's the magnetic field H, but there's also another magnetic field called the magnetic flux density, which is denoted by the symbol B. And the two are related to each other. If you take the magnetic field H and multiply it by the permeability mu, then you end up with the magnetic field B. That magnetic field is important in the next slide. Here we see the slide that depicts pictorially Faraday's law, another important law in electromagnetics. And what Faraday's law says, that if you have a magnetic field B that varies as a function of time, then you have an electric field E that circulates around it. So here, the green lines are the magnetic field, and the electric field E circulating around it is the dashed red line. This time-varying magnetic field is very important. And I've denoted the time-varying field by writing the time derivative dB by dt. If it varies as a function of time, then the time derivative is non-zero. In order to emphasize the fact that the magnetic field varies as a function of time, I've made it flash, because a flashing field is one that changes as a function of time, just as the magnetic field must change as a function of time in order to induce an electric field around the magnetic field. So whenever you see a flashing magnetic field, you know that an electric field will be circulating around that magnetic field. The type of apparatus that we use in controlled source electromagnetic methods has a transmitter and a receiver. The transmitter, shown on the left here, is denoted TX. It's comprised of a wire loop, and current flows around that wire loop. Remember from Ampere's law, whenever you have current, you have a magnetic field that circulates around it, shown here with the green lines. This magnetic field, called the primary field, because it comes from the transmitter, is both above the ground surface and below the ground surface. The ground surface here is the black line. So the magnetic field goes down into the ground. If the current flowing around the transmitter varies as a function of time, then the magnetic field that's proportional to it will vary as a function of time as well. So in that case, the primary field varies as a function of time, so you can see that it's flashing. Remember, a time-varying magnetic field, according to Faraday's law, has an electric field that circulates around it. And I've drawn some electric fields circulating around it down here. The electric field actually circulates everywhere, but I've just drawn it in that region, because that region, as you'll see on the next slide, is a zone where there is some conductive material. Here's the conductive material inside this feature, or inside this circular thing you see here. So inside there, the conductivity is non-zero. The electric field is also non-zero. So when you take two non-zero numbers and multiply them together, you get a current density J, which is non-zero. So that electric field has become a current inside that isolated conductor. And remember from Ampere's law, whenever there's a current, there's a magnetic field associated with that current, and you see that on the next slide. This magnetic field associated with the current flowing in the isolated conductor is called the secondary field, and the secondary field extends back up above the surface of the Earth, and that field can be measured by the receiver. The schematic diagram that I showed you on the previous slide is a generic type system, but now I'm going to talk more specifically about an airborne electromagnetic system. And in this case, the transmitter is on an aircraft, and the receiver is towed behind the aircraft on a long cable. It's 137 meters long. Also towed behind the aircraft on another cable is a magnetometer, and that magnetometer measures the strength of the Earth's magnetic field. That magnetic field is the same magnetic field that deflects a compass needle. So previously I explained how currents were induced in isolated conductors below the ground surface. Now I want to talk about the case when all the material below the ground surface is conductive. So here we have an airborne electromagnetic system flying above the ground surface, depicted with this thick grey line. Current is flowing in the transmitter, and then that current switches off suddenly. Because the current switches off suddenly, the magnetic field will switch off suddenly, so it's changing as a function of time. So that means we should make it flash because it's time varying. And remember, whenever you have a time-varying magnetic field, according to Faraday's law, you get an electric field that circulates around it, and you'll see that on the next slide. So here's the electric field circulating around the time-varying magnetic field. It's the red circle that you see. So that's an electric field, but remember, all this material below the Earth's surface is conductive. So electric field multiplied by conductivity gives us a current density. So that electric field becomes a current. And remember from Ampere's law, whenever you have a current, you have a magnetic field associated with it, and you're going to see that on the next slide. So there's the magnetic field. It's depicted as red. Now this current that you see flowing here has a certain amount of energy associated with it, but the energy associated with that current is transferred to the rocks in the ground in the same way that energy in your stove element, your electric stove element, is changed into heat. The energy in that current flowing in the ground is also changed into heat, and so the amplitude of the current will decrease. As the amplitude of the current decreases, the amplitude of the magnetic field associated with it decreases as well. So that means that magnetic field has to vary as a function of time. This slide shows the electric field circulating around that time-varying secondary field. Notice that it's a little bit deeper and a little bit broader. Once again, that electric field, it becomes a current and has another magnetic field associated with it, which is also broader and deeper, which you'll see on the next slide. This magnetic field here decays away as well because the currents that it is associated with are decaying away too because of resistive losses, and so this magnetic field is time varying as well. So you can see it flashes and an electric field will be induced circulating around it according to Faraday's law, and you see this on the next slide. Once again, notice that the electric field is now deeper and broader than the previous two examples. So, just to summarize, current in the transmitter loop is switched off, and that induces currents in the ground, quite close to the ground surface, and fairly compact. The decay of these currents induces other currents in the ground that are deeper, as you see on the next slide. And these currents decay away and induce other currents deeper again, as you see on the next slide. So the airborne electromagnetic system induces currents in the ground that penetrate down as a function of increasing time after the current in the transmitter is switched off. There's an approximate formula that allows you to calculate what the depth of the currents are, and therefore how deep the electromagnetic system can see into the ground. And the skin depth, delta, is given by this equation here, 0.55 multiplied by the square root of the resistivity multiplied by the delay time and divided by the permeability. So I've calculated what the skin depth is for a number of different delay times and resistivities and put them on a table in the following slide. So this particular table is for a delay time of 3 milliseconds after the current in the transmitter has switched off, and you can see that the skin depth varies depending on what the resistivity is. Typically, rocks in a sedimentary basin will have resistivities of the order of 10 or 100 ohm meters, and this corresponds to skin depths or depths of penetration of between 85 and 270 meters into the ground, which isn't that deep. You can look a little bit deeper into the ground if you go to a later delay time. The next slide shows the depth of penetration for 30 milliseconds. And on this slide you can see that the depth of penetration has increased by about a factor of 3. So now I want to show you some real data collected in the field. And first I'm going to show you some slides of the real electromagnetic system that collected that data. And this is the aircraft that the Airborne Electromagnetic System is mounted on. It's a CASA, twin-engine aircraft. And the wires that you see strung around the periphery of the aircraft is the transmitter loop, and the current flows around these wires. The transmitter loop is out as large as it can be, because the larger the loop is, the stronger the field that penetrates into the ground. This is a close-up of the transmitter loop from underneath the wing of the aircraft, and you can see that there are 6 wires that comprise the transmitter loop or coil, and the more wires you have, the more current that there is flowing around. These wires are quite thick. They're about as thick as your thumb, and they carry hundreds of amps. The receiver coil is in a housing. You can see 2 housings here. The right one is the receiver coil. The one on the left contains the magnetometer that's used to measure the Earth's magnetic field. These housings sit here just below the aircraft when the aircraft takes off and lands. On the next slide, you'll see where they are when the aircraft is flying at survey altitude. So here you can see the aircraft on the left with the EM transmitter on it, and then 130 meters behind and 50 meters below, you see a tiny little white dot. That's the EM receiver. And then you can see another tiny little white dot. That's where the magnetometer is. So that's what the EM system looks like when it's flying. This slide shows how the current flowing in the transmitter varies as a function of time. The bottom axis is time. The vertical axis is current. At 0 time, we have 0 current flowing in the transmitter, and then the current builds up, reaches a peak, and then switches off suddenly. And then after that, the current is 0 and flat for a certain amount of time, called the off time. This time-varying current generates a time-varying field that induces currents in the ground according to Faraday's law. And And this slide shows when measurements are taken, both during the pulse. These are called on-time measurements, and they're made in 5 on-time windows. And then there are measurements that are taken in the off-time, and you can see that these measurement windows are numbered 6, 7, 8, 9, 10 through 20. The ones that are very close to the switch off are called early time windows, and the ones that are far away, 18, 19, and 20, are called late time windows. The way the current switches on and then off again in this shape of half a sine wave, as is done with the G10 and megatem waveforms, is not the only way that current can switch on and off. There are a variety of other electromagnetic systems, and each have their own unique waveform shape. The important point is that the waveform has to vary as a function of time, so that Faraday's law can induce currents in the ground. So I've spoken a little bit about the physics, the laws that are important in electromagnetics. I've spoken about the instrumentation. Now let's talk a little bit about the geology and how the geophysics can infer the geology. And what it infers is the resistivity. And you can see here that there's a very large range of resistivities from 0.001 ohmmeters up to 100,000 ohmmeters, and different rocks span this whole range of resistivities. That means that we get different types of decays for different rocks. For example, if we have a good conductor, currents like to flow in that good conductor. You get very small resistive losses, and the currents continue to flow for a long time, so the magnetic field associated with those currents decays away slowly. So you can see the red curve here decays away very slowly, being larger at late times. Something that's not quite as conductive, a moderate conductor, for example, has more resistive losses, so the magnetic field and the response decays away more quickly. A poor conductor has high resistive losses, so the magnetic field and the response decays away very quickly, as you can see by the black line here. If you want to measure that very fast decay, you need very narrow windows close to the switch off in order to be able to take those measurements. This is some electromagnetic data collected by an airborne electromagnetic system. The top graph is the data collected along a profile. The profile starts at 0, 1,000, 2,000, 3, 4, 5, 6,000 meters along the profile, and the vertical axis shows the magnetic field in femtoteslas. There are a number of black curves on this profile plot. The black curve with the largest amplitude is the response that's measured in the window that's closest to the switch off. That's window number 6. The second black curve is the response that's measured in window number 7. The third black curve is measured in window number 8, and so on down to the very smallest amplitude black curve. That's the one that's measured in window number 20. So you can see that the response at one location starts off at larger, say at around 5,000 on the profile, starts off large and decays away to be very small. So that's a moderate conductor there, because it starts off large and decays away to be small by the latest delay times. At other locations, for example near 3,000 on the profile, the response starts off smaller but remains larger at late delay times. So this is a better conductor here. The black curves, as you see on the top plot, can tell an experienced geophysicist where the resistive and the conductive zones are, but sometimes it's better to take that data, magnetic field as a function of delay time, and convert it into something that looks more like the geology. On the bottom panel that you see is a resistivity depth section derived from the data above, and this gives a better indication of what the geology looks like. Blue zones are resistive and red zones are conductive, and you can see that there's a conductive zone below about 700 meters deep. And the most conductive zone on the section at around 3,000 meters corresponds to the very red zone at about 1,000 meters depth. And this is consistent with drilling information that was done in this particular zone. I just want to explain briefly the process that is used to generate this resistivity depth section. What you do is you look at the response at a certain location on the profile. It'll be a magnetic field at a particular delay time. You work out the resistivity of a half space that would give you that response at that particular delay time. You know the resistivity, you know the delay time, you can work out the skin depth, so you color the section, a color that corresponds to that resistivity at that skin depth. And then you repeat the process for the next delay time, which will give you something a little bit deeper, and then the next delay time something a little bit deeper. And so at one location, you color the section below that location, and then you repeat that process for other locations until eventually you build up a color section for the whole profile, which is what you see here, a resistivity depth section, which is a useful way of looking at this type of data that looks more like the geology. I want to show you one example from mineral exploration, because airborne electromagnetic methods are used very extensively in mineral exploration, and they have been for more than 60 years. This particular example is from the Voisey's Bay deposits, which is a very rich set of nickel deposits in Labrador. And the profile I'm going to show you is across the ovoid, which is one of the richest zones at Voisey's Bay. And here you can see in cross-section the black blob is the ovoid, and then above that is the electromagnetic responses. And there are good, strong electromagnetic responses in the vertical Z and the horizontal X components of the geotherm, and there's also strong responses in the helicopter electromagnetic profiles. You can also use airborne electromagnetics to map the geological features. This particular electromagnetic data set was collected in the Bathurst mining camp of New Brunswick, and we can see that there's some interesting fold-like features at the top part of the map, and then some other zones on the eastern side of the map, which are yellow and therefore more conductive. So that's the electromagnetic map. The next slide shows the magnetic map collected at the same time. And you can see that this magnetic map shows you similar fold-like features at the top, but in other places it's quite different. For example, it's very quiet on the eastern side, where there was a yellow zone previously on the electromagnetic data set. This electromagnetic data and magnetic data can be used to make inferences about the geology, and when you combine that with geological mapping, actually looking at the rocks on the ground, you can use the geophysics to help you build up a geological map, which is what you see on the next slide. Here's the geology, and notice the fold-like features at the top and other features. If you flip through these slides, they're all positioned so that they're roughly in the same place. You can get a good idea of how they compare. I want to just touch briefly on how electromagnetics can help to look for kimberlites. Kimberlites are very valuable because they contain diamonds in them, and so people use geophysics to look for kimberlites, and electromagnetics is a powerful tool. This particular example is from Saskatchewan, where some magnetic data was used to infer that there might be some kimberlites. This magnetic data was very old data, collected in 1969, and it wasn't looked at until the 1990s to see whether or not there might be a possibility of kimberlites in it. These anomalies that you see here were potential kimberlites, and so this ground was staked by Uranotes, and then some follow-up work was done, and that follow-up work included some electromagnetic data. On the left you see the magnetic data, which is much better quality than the much older data, because the magnetometer was closer to the ground and therefore collected higher resolution data, and the lines were closer together, so we get much sharper features. So each of the distinct blobs that you see on the magnetic anomaly map are kimberlites. And where each of these kimberlites are, you can see if you look at the electromagnetic map, which is on the right, that there are blue zones. So in this case, the electromagnetic data is providing complementary but confirming information about the kimberlites. And it's not very obvious whether the kimberlites are on the electromagnetic data when you look at it in this form, but if you look at resistivity depth sections, as you see on the next slide, then you can understand a little better what's going on. So here are a number of resistivity depth sections for a number of profiles. And if you look at the fifth one down, 1, 2, 3, 4, 5, you'll see that there's a blue zone at the top, that's resistive rocks, and then there's a red zone, those are conductive rocks, and then as you move across towards the middle of the profile, you notice that it turns yellow, and that's a relatively more resistive zone within that red zone, and that's the more resistive kimberlite. So the kimberlite has intruded through that conductive sequence there, and it's a more resistive zone. Returning now to our diagram that shows the resistivity of different rocks. We've talked about sulfides, and we've talked about a graphite example. The first example I showed you was a graphite example. Now I want to talk a little bit about saline water. The example I'm going to show you is from Denmark, where you have a geological section that looks like this. There are tills and sands in the top 5 to 80 meters, and then there's a bryozo limestone which contains fresh water. Both the till and sands and the freshwater limestone are resistive, and then there's an interface, and then below that interface there's bryozo limestone, but now it contains saline water. And this saline water is very conductive. So it's possible with airborne electromagnetic methods to estimate what the thickness of the glacial tills and freshwater are, and therefore the depth to this interface. So we can estimate the thickness of the freshwater aquifer. And when this was done for an area in Denmark, we got the map that you see on the following slide. This is the survey area, and the colours denote the thickness of the aquifer. So blues are thin aquifers, and yellows and oranges are thick aquifers. So now the Danes know where the most fresh water is. It's in the yellow and orange zones. So this is an airborne electromagnetic survey that was used to acquire this data, and it was acquired in about 2 or 3 days. The thicknesses of the aquifer, as estimated from the airborne survey, were checked against the thicknesses determined from a ground survey, and there's very good agreement. The colours inside the circles are from the ground survey, the colours outside the circles are from the airborne survey, and you can see in most cases the colours inside and outside agree. The interesting thing is that it took about 2 days to collect the airborne data, but it took many, many weeks to collect the ground data. So it can be a lot more efficient to survey for groundwater with an airborne method. Now I'm going to talk a little bit about how airborne electromagnetic methods can detect paleochannels. And this diagram just shows how paleochannels are created. We have some glaciers melting, the meltwater is flowing away from the glacier and creating these channels. And then the glacier will melt away completely, and then there'll be another wave of glaciation, and then when that glacier melts, everything that you see here is covered by more sediments. So these channels become obscured and therefore paleochannels. And you can't see them when you just look at the ground surface, but you can see them if you use some geophysical methods. There are many areas where there are paleochannels in Alberta, and I'm going to be showing you some data that was first published by Richard Kellett in the CSEG Recorder, and this data is from the Utakuma area. So here's the geophysical data. On the top there's seismic data, and on the bottom there's electromagnetic data. So there's Cretaceous rocks, and then there's Quaternary rocks. And the Cretaceous rocks you can recognize have looked to be flat-lying because the seismic reflections are flat-lying. And then you can look at the Quaternary rocks, and you can see that the seismic signature from the Quaternary rocks is quite chaotic. So drawing a red line between the Cretaceous rocks and the Quaternary rocks, you can see that there's a number of places where the Quaternary rocks thicken, and these are paleochannels. I should point out that this seismic data was quite expensive to collect because you need a high-frequency source, you need small group spacings, and you need both small and large offsets in order to get good enough signal-to-noise. The section on the bottom is derived from the electromagnetic data, and in this case, the Cretaceous rocks are very conductive, and the Quaternary rocks are more resistive. The top of the blue zone is the boundary between the Cretaceous and the Quaternary, and you can see that there are a couple of places where the Quaternary thickens. These are the paleochannels, and they correspond in the seismic data and the EM data. So the EM can be used to find these paleochannels. This slide is shown courtesy of Synovus Energy, who gave permission to show this at the CSEG Distinguished Lecture. And on it you can see some features that look like paleochannels. There are some river-like features running through the area. And these features, sometimes they can be interesting because there's gas in them. Some people drill shallow wells and pump gas out. It's quite cheap to do that. And if the wells are close by to nearby gas pipelines, then and the price of gas is high, then you can make a little bit of money doing that. However, there are other reasons why you might like to know where there are paleochannels. Let's say, for example, that you want to drill a deep well in order to explore for hydrocarbons, but in doing so you go through a paleochannel and there's a lot of water in it, then you can get a flood, as you see on this particular slide here. And this flood causes quite a bit of damage and is expensive to clean up. If the paleochannel contains gas and you try and drill through it and the gas accidentally catches fire, then that can create a catastrophe. In this case, there was an incident that resulted in a fire and a fatality. And you can see again that causes quite a bit of damage. And obviously you want to avoid this. And here's another example that shows some damage created when a paleochannel contained gas. These examples are courtesy of Synovus Energy. You can also use airborne electromagnetics to look for oil sands. The oil sands are relatively resistive, so in the Fort McMurray area, near the Athabasca River, you can map the oil sands. But as you move to the south on this section, you get more conductive clearwater shales above the oil sands, and when these clearwater shales get quite thick, it's not really possible to penetrate very deep through the shales and to map the oil sands below. Particularly even further to the south where you get the Grand Rapids, which are also thick and conductive. when extracting oil from the oil sands, an important thing that's required is water. And airborne electromagnetics can help people look for water. And here we show an example of some airborne electromagnetic data that was collected in a certain area. And you can see that the orange features that have been mapped correspond to aquifers. And the best method for finding aquifers is the resolve system, because it's identified a very small aquifer here that the other types of electromagnetic systems haven't identified. However, the other electromagnetic systems can see a lot deeper, so each has their own advantage. My final example in this presentation is how airborne electromagnetics can help the mining engineers plan the extraction of the oil from the oil sands. This particular survey was flown in an area where two different modes of extraction can be used. On the east of the survey, the oil sands can be dug up because they subcrop. However, on the west of the survey, the Clearwater Shale subcrops, and so it's necessary to drill holes through the Clearwater Shale and pump steam down and extract the oil using steam-assisted gravity drainage. So you can see, in order to plan how to extract the oil from the oil sands, it's important that the engineers know where there's a Clearwater Shale that subcrops or where there's a McMurray that subcrops. Prior to this survey being flown, this red dashed line was believed to be the line that indicated where the McMurray was to the right and the Clearwater was to the left. An airborne electromagnetic survey was then flown, and it was found that there was conductive material associated with the Clearwater that was both to the left and to the right of that line, and so the black line was drawn, and that black line is believed to be the demarcation between where the Clearwater subcrops on the left and the McMurray subcrops on the right. So you can see now the engineers have better information to plan the extraction. As a bonus, some other information came out of this survey. It was noted that the orange zones were more resistive, and these corresponded with the bituminous-rich zones, whereas the other purple zones tended to be associated with places where there was more clay and less oil in the oil sands. So knowing where the richer deposits are and where the poorer deposits are, again, the extraction process can be optimized to be most efficient. So you can see EM has helped in this particular case. So this is the summary slide. I hope that I've explained a little bit about the physics of electromagnetics to you and explained a little bit about the geophysical systems and convinced you that airborne electromagnetics can map the conductivity and the resistivity, but only in the top few hundred meters. I hope I've shown that airborne electromagnetics can be used for sulfide exploration, for uranium exploration, when it's associated with graphites, and also for kimberlites. Airborne electromagnetics can be also used to help for groundwater and to find places where there's more fresh water, to map the freshwater saline water interface. You can use it to map porosity in some cases. You can use it to identify dry land salinity for waste studies and also to look for unexploded ordnance. You can map paleochannels with airborne electromagnetics. In some cases, the paleochannels might contain gas. In other cases, they might contain coal or water. The gas can be something that's worth extracting, or it could be a drilling hazard. It depends on your perspective. And finally, you can use electromagnetics in the oil shales, both to look for bitumen, to define the impermeable cap, and also to look for water that's used in the process of extracting the oil from the oil sands. So, thank you very much for listening to this talk. I'd also like to thank the organizations that made this talk possible. The CSEG sponsored the Distinguished Lecture Tour. Thank you to them. Also, a lot of the work that was done in this talk was done when I was working at Fugger Airborne Surveys, and thank you to Fugger Airborne Surveys for their assistance. And also thank you to the organizations that I'm associated with now, the Center for Excellence in Mining Innovation and Laurentian University. Thank you.